Hi, I'm going to present our work on learning a better control barrier function. Safety is one of the most critical aspects when designing a controller, and control barrier functions provide a simple yet effective way to synthesize controllers for safety-critical applications in a minimally invasive fashion. In this work, we consider system dynamics in the control affine form, where X represents the state, Fx represents the drift, Gx represents the control influence matrix, and U represents the control. In this setting, safety is represented as the satisfaction of a few constraints. Each constraint are in the same form, Cix less than or equal to Bi, or can be rewritten as Bi minus Cix greater than or equal to 0. Written in this form, each constraint forms a zero superlevel set where each state in that set satisfies these constraints. Then the safe set C can be seen as the intersection of all of these superlevel sets of each individual constraints. Now we define the notion of forward invariance. For every state at time 0, if it belongs to a set C, the system is considered to be forward invariance with respect to that set if we have X at each time step T also belonging to set C. In the context of safety, if C is a safe set, then once the state belongs to the safe set, if it is forward invariance with respect to the safe set, that means it will never exit the safe set, which we can then say the system is safe with respect to that set. With these notions in mind, we can define a control barrier function. First, we can see control barrier functions as a safety certificate, assuming we have a control barrier function Hx, such that for each state that belongs to C, the control barrier function should satisfy Hx is greater than or equal to 0 within the safe set and less than 0 outside of the safe set. If that is the case, then we can use this control barrier function to certify safety for states. So let's say we have a state Z, and by computing the value of Hz, we can see whether it's safe or not. If it is safe, then the value of Hz will be non-negative. If it is not, then Hz will be negative. Another way to use control barrier functions is to use it to synthesize control actions. To do this, we will utilize what is called a control barrier function constraint, which is in the form of partial h partial x times fx plus gx times ux, and making it greater than or equal to minus alpha hx, where alpha is a class K function. If such a control U exists for each state in the safe set, then we can call hx a control barrier function. So the standard way to utilize control barrier functions for synthesizing safe control actions is to do what's called a CBF QP. To compute the CBF QP, we usually utilize a performance controller uref and formulate the CBF QP as minimizing the least square distance between uref and U, subject to the CBF constraint. And the solution to this QP is the closest controller in least square sense to uref that also satisfies the CBF constraint, which we also say that the controller alters uref in a minimally invasive way to ensure safety if we see the CBF QP as a filter on top of the performance controller. And in this case, the performance controller ensures task completion while the CBF constraint ensures safety. Now we're going to talk about the problem formulation. It is well known that constructing a control barrier function that covers the entire forward invariance part of the safe set is very difficult. However, constructing only a subset of the safe set, recovering only a subset of the safe set using a control barrier function is usually manageable, even if the control barrier function is handcrafted. We call these handcrafted CBFs HCBFs, and we denote them using a hat, H hat, and we also define the zero superlevel set of a handcrafted CBF as C hat, which is usually a subset of the true safe set C. And without loss of generality, we can assume the relationship hx is equal to the handcrafted CBF h hat plus a distance plus an error delta h. And the goal of this paper is to find a way to estimate delta h. And now we show our proposed method to do that. Assuming we have a data set of safe and unsafe states, which will cover the collection process later in the next two slides. Assuming that we already have that data set, we are going to estimate delta H using a neural network. Now we show the loss functions we use to learn that neural network. So the loss function we use basically tries to enforce the CBF conditions. So the first condition is for all states in the safe set, the CBF value should be positive. And to enforce that, we use the loss function LH. If we look inside the summation, it's basically the max between 0 and minus the estimated CBF. So here, if the estimated CBF is negative, which has the wrong sign, if we put a minus sign in front of it, it will be positive, and we'll have a positive loss for that term. However, when it is positive, which means it has the right sign, then the negative of a positive number would be negative, and then the max would simply be 0, and it will incur 0 loss. So what this loss function does is basically only penalizing CBF estimations that have the wrong sign. Similarly, we have the loss function for CBFs of the unsafe states, where we only penalize CBF estimations that are positive, which they should be negative. And we do the same thing for the CBF constraint. So if we just move the alpha hx to the left, we can see the entire inequality should be greater than or equal to 0. And we put that into the loss function, and we can get a formulation very similar to condition 1. Although these are the only conditions that a CBF should satisfy, we can add additional constraints to guide the learning process. To do that, we use what's called a distance function, dx's, and these dx should be continuous and increase as it moves inside the safe set and decrease as it moves out inside the unsafe set. And the first condition simply becomes hx greater than or equal to d plus x. And what if we put d plus x inside the loss function, we have the new loss function LH. And we can do something similar for the unsafe loss, while we keep the CBF constraint loss the same. And in our case, there are much more safe data than unsafe data. Thus, we need to also ensure that the learned CBF does not simply output a positive value for any state. This can be achieved by regulating the change introduced by delta H hat. The logic behind this choice is that for unsafe states, the handcrafted CBF already gives them a negative value. By regulating the change introduced by delta H hat, we aim to only make the CBF values for the safe states positive while keeping the unsafe states negative. To achieve that, we add another loss function, L delta H, which penalizes the change. And then the final loss function is simply a weighted sum of all these 4 loss terms. As mentioned before, the learning process requires both safe and unsafe data. However, collecting unsafe data may be costly in many cases, such as in autonomous driving. So instead of finding an unsafe controller, we perform model-based rollouts to generate fake data. We use a CBF QP controller with the learned CBF during training to collect safe interactions. Note that unless we have a control barrier function that is fully trained, there is no guarantee that the learned CBF corresponds to a safe set. To deal with this issue, the controller performs a rollout using the CBF QP controller every couple steps. If the rollout generates unsafe data, the data is recorded and a model predictive controller is invoked to generate safe control actions. Using this approach, we can obtain safe and unsafe data without subjecting the real system to unsafe conditions. In addition to the model-based rollout, mentioned above, a model-based rollout can also be performed when the system is close to the constraint boundary. To check if the current state is close to the constraint boundary, we define a value epsilon c. And whenever at least one of the entries of cx minus b is larger than minus epsilon c, a model-based rollout is performed. And in this case, the rollout is performed using the performance controller, which is generally an unsafe controller. The model predictive control formulation we use is as shown in this slide. The objective function is simply to for task completion, while it's subject to an equality constraint for the system dynamics and the same safety constraints as the CBF needs to enforce. Since training is performed offline, the computational cost of using a model predictive controller can be mitigated by using simulation environments or more computational resources than during inference. And once the controller is fully learned during inference time, only the learned CBF QP controller will be utilized. Now we're going to show the effectiveness of our approach using two simulation studies. The first task is a second-order integrator target reaching task with velocity constraints. This is a toy example where the learned CBF can be plotted and analyzed. So here, the system dynamics is shown as follows. X represents the position, x dot is the velocity, x double dot is the acceleration, and u is the control. The safe set is described by the constraints x dot less than or equal to 3.0, and the handcrafted CBF has the form of 2 minus x dot, which corresponds to the constraint x dot less than or equal to 2. And the distance function are shown as given as 3 minus x dot. The MPC formulation we use has a quadratic cost and subject to system dynamics and initial condition constraints, and also the velocity constraint. The result using the learned CBF controller is shown as follows. If we look at the lower left plot, we can see the quality of our learned CBF. It can be seen in most of these state space, the learned CBF does find the correct sign, and the zero super level set closely resembles the ground truth zero super level set. There are inaccuracies in estimating where the zero level line should be when x is close to minus 15 and 0. And this is due to having no data when the velocity is close to 3 meters per second at the beginning and at the end of the trajectory. For more details regarding the experimental setup, please refer to our paper. The second task is a ball on beam balancing task with angle constraints. And this study demonstrates how to use our approach on a nonlinear system. The dynamics of the ball on beam system is shown as follows, where beta is the beam angle and r is the position of the ball. The constraints of this experiment is beta less than equal to 0.75 and beta dot greater than or equal to minus 2.5. We craft a handcrafted CBF in the form here shown on the slide. This handcrafted CBF corresponds to the constraint beta less than or equal to beta bar, and the distance functions are shown as follows. The ball on beam MPC formulation is very similar to the second order integrator example, where the cost is a quadratic cost. The main difference is that here the system dynamics is nonlinear, and it is also subject to initial condition constraints and velocity, angular velocity and angle constraints. This figure shows the trajectories generated using our learned CBF controller subject to different values of gamma. So here the function alpha is simply gamma h, and we can see that as gamma gets increased, the trajectories approaches the constraint boundaries more aggressively, which is the same as what the theory suggests. And also for the CBF values, as gamma increases, the lowest CBF value along the trajectory gets closer to 0. Thank you for listening to this presentation. If you are interested in our work, please refer to our paper.